This next grouping of lectures deals with electrons. And the reason we deal with electrons is that's where all chemistry occurs. In order to understand how chemical processes occur, it's helpful to know where the electron lives or resides. And that is called the electron configuration. We're going to utilize the quantum modification of the Bohr atom. And knowing the electron configuration helps in multiple ways, one of which is explaining periodic trends, another is explaining chemical reactivity, and another is explaining atomic ionization. Now we'll start with the Bohr atom. And the Bohr atom is the atom that is classically taught at the physical science biology level. And that's the one where you've got the nucleus at the center, and then electrons at specific levels around the nucleus in what sort of looks like planetary orbits. Now, the Bohr atom states that electrons can only exist at specific distances from the nucleus. Those are called orbits or primary energy level or shells. It's frequently abbreviated capital or lowercase n, and I tend to use capital N. It turns out there's a maximum number of electrons you can have in any orbit, and the formula for that is the number of electrons per orbit is equal to the orbital level n squared multiplied by 2. So looking here, we would say that this is the second orbit. So 2 times 2 squared equals 8. And so we would say the second level can hold 8 electrons. And you may have heard or seen the 2, 8, 18 rule, which is the number of electrons can be in the first orbit, the second orbit, and the third orbit, and this is where it comes from. Now, there is a quantum modification of the Bohr atom. This is based upon complex mathematical calculations. You will not need to do these calculations in regards to probabilities. It turns out we really don't know where electrons are. We can just calculate where they're likely to be found. However, this ends up breaking the orbits into smaller units called orbitals. And there are 4 types of orbitals: S, P, D, and F. There actually is a rational reason why they are called S, P, D, and F, but we're not going to go into it. The number of orbitals in any orbit is equal to n, or the integer of, and orbitals are ordered first S, then P, then D, then F. So if you look at this, n has 1 orbital. So following this, n equals 1 has an s orbital. It has 1 orbital. N equals 2 has 2 possible orbitals, S and P. N equals 3 has 3 possible orbitals, S, P, and D. 4 would be S, P, D, and F. Don't worry about what happens at 5 and beyond. Now, each orbital can be subdivided into suborbitals. Now, you need to memorize this. S can have 1 suborbital, P has 3, D has 5, and F equals 7. Notice the number of suborbitals goes up by 2 for each one. And each suborbital can hold a maximum of 2 electrons. So any s suborbital can hold a maximum of 2 electrons. P can hold a maximum of 6 electrons. D can hold 10. F can hold 14. And once again, this does need to be memorized. Now, there are 3 rules for placing electrons. Rule number 1, fill the lower energy orbitals first. This is called the Aufbau. Rule number 2, all suborbitals must have an electron before you can double up within a suborbital. That's called Hund's rule. The third rule, electrons in the same suborbital must have what is called opposite spin. Spin is usually shown by an arrow, and we'll say that something has spin up or spin down. So if you have 2 electrons in the same suborbital, one must be spinning up, one must be spinning down. That's called the Pauli principle. Now, 2 and 3 are very easy. The first one is a little confusing. You don't just fill up n equals 1 of the first orbital, then fill up the second orbital, then fill up the third orbital. The orbitals fill up in a non-obvious manner. And there are 2 ways to know how the orbitals fill. There's a mnemonic, or you can use the periodic table. I'm going to show you both. For the mnemonic, you're going to build a grid that looks like this. When you go to do your configuration, you're going to draw diagonal lines. You're going to start at the 1s, and you draw a diagonal. Then you go up 1, draw the diagonal. Go over 1, draw the diagonal. Up 1, over 1, up 1, ad infinitum. So suppose we wanted to know what the electron configuration of potassium is. We would follow the mnemonic. The first thing you do is identify that potassium has an atomic number of 19, so it has 19 protons, and thus has 19 electrons. So I draw my first line that cancels out the 1s. That holds 2 electrons, so I subtract 2. I now have 17 electrons left, and I can write 1s2. Go up 1. I can put 2 electrons into the 2s2. Subtract the 2, write down the 2s2. Over 1, go to 2p6. I can put 6 electrons there, but I still have 9 electrons to place. The next 2 go into the 3s, 3s2. Then I go 3p6, 4s1. So we would say that the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So what is the electron configuration of bromine? Stop, figure it out, come back, check, and we'll go from there. Go. And this is what you should get for the configuration. And one of the things to notice is you go from 4s to 3d to 4p. How does that happen? You follow the mnemonic. So bromine has an atomic number of 35. So it has 35 protons, which means it's got 35 electrons. So I need to start placing them. I start here with 1s2, so I'm going to put 1s2 here. 35 minus 2 is 33. I go up 1. I can place another 2. 2s2, subtract another 2, and I now have 31 electrons to place. 2p6, so I can take away 6 there, and that's 25. I can continue to 3s2, so I can lose another 2, and that's 23. I'm going to put the 23 over here. So I've gone up 1, over 1, time to go up 1, 3p6. I'm going to take away 6. That gives me 17. After 3p comes 4s2. And that's 15. Up 1, over 1, up 1, so go over 1. Oh, wait a second. 4s, now I have 3d. 3d10. I subtract 10. I have 5 left. I go to 4p. 4p can hold up to 6, so it can easily hold the 5. I now have my electron configuration, which is the same as this. Okay, there is another way to do this, and this is to utilize the periodic table. When you look at the periodic table and you look at the shape of the periodic table, it can be broken down into 4 sections: the S block, the P block, the D block, and down here is the F block, but we're not going to worry about the F block. And we can fill these going across, and we can read off the configuration. So let's do this with an example. What's the electron configuration of germanium? Well, find germanium and you see it's there. 32 is the atomic number, so it has 32 electrons. I go to my top row or period, and I see I can place 2 electrons there into the s orbital. So I can write 1s2, and now I have 30 electrons left to place. I drop down to the next period. I can put 2 electrons into the s block, so that would be 2s2. I move over, and I can put 6 electrons into the 2p block. That is 2p6. Now I have 22 electrons left to place. 2 in the 3s, so I have 20. 6 in the 3p, so now I have 14 electrons. I put 2 into the 4s, so now I've got 12 electrons left. But notice I'm now going to be crossing the D block, and the D block starts on the 3rd level. I can place 10 electrons there, so that's 3d10. My last 2 electrons get placed there. So I can say that this is the electron configuration of germanium, read off the periodic table. Now that's a lot of writing to do. We sometimes talk about the abbreviated configuration. The abbreviated configuration consists of 2 parts: the noble gas from the period above, and then the remainder of the configuration. This is easy to read off of the periodic table. So let's take a look at the abbreviated electron configuration for tellurium. There's tellurium. Don't even need to worry about the fact that it has an atomic number of 52. I identify the noble gas in the period above, which here is krypton, so I write krypton in square brackets. I go back to the periodic table, and I go to the period that tellurium is in, which is the 5th. I can now say I have 5s2, 4d10, 5p4. That is the abbreviated configuration for tellurium, and that is a whole lot easier and quicker to write than going through all of that. Both of these state the same thing. Now, here's a key point for the exam. Unless you are specifically asked for the abbreviated electron configuration, write out the complete electron configuration. So that's the introduction to electron configuration. To review, electrons can only exist at specific distances from the nucleus. These are called orbits or primary energy levels, and are abbreviated with a capital or a lowercase n. There is a maximum number of electrons per orbit, and the equation is the orbit number squared times 2. Orbits can be divided into orbitals. You have S, P, D, and F. The number of orbitals in any orbit is equal to the primary energy level of that orbit. You add orbitals to a orbit in the order of S, then P, followed by D, followed by F. N equals 1 has an S, N equals 2 has an S and a P, so on and so forth. Every orbital can be divided into suborbitals. Each suborbital can hold a maximum of 2 electrons. So the S orbital can hold 2, P can hold 6, D can hold 10, F can hold 14, but they don't have to be totally filled. You're going to figure out how to fill the orbitals and in what order using either mnemonic or the periodic table. The more you use the periodic table, the easier that becomes. So there is a lot to memorize in this video, so you will need to be like the proverbial elephant and never forget. In the next video, we're going to start to talk about periodic trends, and electron configuration will play into that.